So anyway, as I was saying before this stopped without me asking it to stop, um, radiation does not require a medium to travel through. It can travel through things. It can travel through the air. It can travel through liquids. Radiation can even travel through solids. Not all solids. Some solids have a tendency to block radiation or reflect radiation, but radiation can travel through things, but it doesn't have to. It can actually travel through nothing. It can travel through space. It can travel through a vacuum, for example. And so it is very unique in that way, whereas convection cannot happen in space. Convection has to have some kind of fluid to travel in, to carry it from one point to another, because it's about making things, making molecules or atoms move. Conduction is, of course, the touching of two things. So you can conduct heat in space from one object to another, but heat cannot conduct through space itself, because space itself is nothing. So radiation, however, is different. It can travel through space, and that's exactly how we get our energy from the sun. Our energy from the sun travels through space as light, as radiation. It's pure energy. It has no mass to it whatsoever. And then it goes through our atmosphere. Some of it gets lost by scattering through the atmosphere. Some of it gets lost by being absorbed in the atmosphere, heating up the atmosphere a little bit. Some of it gets reflected off of clouds and things like that. But then the rest of it gets absorbed by the Earth. And then the Earth re-emits that in the form of other types of radiation, which heats up our atmosphere. Right? Now, Mercury is in a very precarious position. Mercury does not have an atmosphere. And the reason it doesn't have an atmosphere is because it's so stinking close to the sun that the atmosphere has literally blown, the sun has literally blown the atmosphere off of Mercury. That's how strong the radiation is on Mercury, because it's just right there. So it's in a little bit of a problem. And Venus is in another kind of problem. Venus has so much atmosphere that the radiation that penetrates Venus never gets out again. Much of the radiation that comes into our atmosphere and hits the Earth escapes again as a different kind of radiation and leaves the Earth again. And there's this nice balance of radiation coming in, radiation going out. But for Venus, for like billions of years, Venus has absorbed all the sun radiation, but it hasn't let any out. Yeah, it's like 600 degrees on Venus. You cook a pizza in 3 minutes, right? Maybe even faster. This is why we're not going to Venus. Some people ask why we're not going to Venus. That's why. Because it's just blinking hot. It's also really high pressure. So we'd get crushed on Venus just trying to walk there. So anyway, the electromagnetic spectrum, which is all the wavelengths that electromagnetism can exist, which is an infinite number of wavelengths, all the way from 0 wavelength up to whatever wavelength being literally the length of the electromagnetic wave. For flames, for things that are on fire, you could think of them as, things that are burning, things that are plasmas. In the spectrum, you have at 6,000 Kelvin, they become red, so they become white hot, as we call it. White hot means something that is burning with a flame that is whitish. So that's what we're looking at here if you look at this flame here. And as you go cooler and cooler and cooler, you come, and white essentially means that it's emitting a radiation that our eyes can't really perceive very well. It's like ultraviolet. Ultraviolet looks kind of like white to us. So that becomes a white hot light. And it's also white hot because it contains a pretty high percentage of other colors in the spectrum. When you mix all the colors, you get white light. But then as you cool it off, you get things that start to look more blue, and then flames that look more green, and then flames that look more yellow, and then flames that look orange, and then flames that look red, essentially. Where 3,000 Kelvin is where we see red flame. So red flame tends to be the coolest of plasmas, and white flame tends to be the hottest of plasmas. And then eventually you can't see it anymore anyway. And it also goes with glowing materials, glowing metals, glowing things. Mostly it's glowing metals, because not many things can get this hot besides metals. But ceramics can and other materials. But For the most part, we're talking materials that can handle these kinds of temperatures start to glow at these temperatures, depending on, and of course, the how they reach those temperatures, how much heat they have to reach those temperatures changes as well. And as we saw yesterday with the tile from the space shuttle, some things will glow red and not even come close to melting, right? Whereas other things will melt when they're glowing red. Once iron starts to glow red, it's getting close to its melting point. But the space shuttle blocks, not so. So here's another interesting thing here. We've got this lighter pavement made of maybe concrete, this darker pavement maybe made of asphalt, and on the darker pavement the ice melts more quickly, right? Why? In this case, both thermal conductivities are the same, so they're going to transfer heat back and forth through the ice the same rates, and they're both the same temperature. They've been in the sun the same amount of time. Well, okay, sorry. They're not necessarily the same temperature, but they have been exposed to the same radiation for the same amount of time. The thing that is different is their temperature. The darker thing actually absorbs more of that light, okay? And the lighter thing reflects more of it. So it's, here they talk about this. You have radiation that comes in, some of it gets reflected, and some of it gets absorbed. In the darker stuff, more stuff gets absorbed, and that's why it looks darker. The things that look darker absorb more light, and the reflected light or the re-emitted light is what we actually see, right? And when the light is coming out of a dark material, when light is emitting out, it emits more light out and retains less light for a darker material. When you have something that is a lighter material, this is being silver coated in this case, it reflects more on both sides. It reflects more on the outside and on the inside. So on either side, either you get a lot of reflection and a little bit of emission for the lighter coated or the lighter colored thing. And you get this one, you get a lot of absorption. And so whenever you get a lot of absorption, you get a higher temperature change. Higher temperatures there. Now this one does have an equation for us. This is called the Stefan Boltzmann law, and it has to do with how much heat is radiated per time for an object that has a surface area of A and a temperature of T. These other two things, this sigma and this E here, are two numbers that you plug in. The sigma is the Stefan Boltzmann constant, which they give you right here. And the other one is the emissivity of the object, which kind of is like, well, it's essentially how well it radiates heat is what you can think of it as. So the emissivity is the radiation factor, I guess you can think of it as. So, and you can also talk about heat transfer as the total heat transfer from a temperature difference of two objects. So you have an object like the Earth in space. What's the heat transfer radiation going to be? You take the temperature of space as one of the temperatures, the temperature of the Earth is another, and then you can calculate that. So if we calculate the net heat transfer of a person standing in a dark room where the ambient temperature is 22 degrees Celsius, the person's skin temperature is 33 degrees Celsius, so there are your two temperatures. Surface area 1.5 meters squared, and the emissivity of skin is 0.97. Emissivity is always between 0 and 1. Okay, so the highest emissivity is 1, and the lowest is 0. Nothing in the universe has either of those emissivities. All things in the universe are either greater than 0 or less than 1. There's no perfect emissivity either way. But you just plug in those numbers, plug them all in, and you get negative 99 watts. The negative coming from the energy is leaving the person's body. You always put the hotter temperature as your second temperature. Well, I guess it doesn't really matter which one you put where. You just have to realize that the heat transfer is going to go from the hotter thing to the cooler thing. And when they did this, I don't actually know if they tell you to do that. Objectivity. So here they say that the object is temperature 1, the surrounding, the environment is temperature 2. And then if you do it that way, where your environment or your surrounding is temperature 2 and the object is temperature 1, then a negative temperature will mean that the object is losing, or a negative heat flow will mean that the object is losing heat, like a person does in a cool room. And a positive temperature would mean that the person's in a warm room and they're getting warmer. They're increasing their energy. So the greenhouse effect, right? This is the greenhouse effect. We have all these different kinds of light coming in from the sun, and the earth absorbs them, but the earth only emits mostly, it doesn't only emit this, but emits mostly infrared light, which actually gets trapped in our atmosphere because of the different molecules in our atmosphere that reflect it. Like carbon dioxide reflects it, so does methane, and we have quite a few of those things from natural processes and some from unnatural processes. And that's what keeps our planet warm. Without this process, we die. Without this process, we would be frozen. And we would never have any heat on our planet. Of course, Venus has this going crazy. It's running rampant on Venus. And on Mars, it's not working hardly at all. Mars's atmosphere doesn't have enough carbon dioxide in it to make this happen. So Mars is freezing. Mars is super cold. Got a whole different problem. But we can use this effect to our advantage in many different ways. We can cook meals with it. This is a solar cooker. It's got a pan in here with some food in it, and it's essentially sealed up, reflective surfaces inside. And it takes a couple hours, and you can cook a nice stew in a solar cooker like this. This is also done in places to purify water. You put a pan of water in here, and then you shape the top of this so that all the water that evaporates and then condenses on the top shield drips down into another pan. And you can purify water that way because the contaminants in the water will not evaporate with the water. So it's a pure water purification method. They call them a solar still when you're doing that. And that takes us to the end of this chapter. We have covered everything. Now I did put the questions in the homework, but the problem was that I found too many questions this time. So there's like 50 questions in your homework, and I'm going to go through and I'm going to pare it down a little bit. I'm going to cut down the questions a little bit. A lot of them are pretty simple, but I'm going to try to cut that down to a reasonable amount, and I will get that out to you. Make that due the end of this week sometime, and then the next homework will be due next week, whatever. So that takes us to the end of chapter 14 rather, and I will have that homework ready for you as soon as I can here today, probably within the next half an hour. I wouldn't start working on it. I don't even know if you can get into it, but I wouldn't start working on it because I haven't cut any of the questions out yet. Oh, it's still locked? Okay, that's good. All right, so where's my, oh, there it is.